Hey everybody, welcome back. We're about to start our second unit, and as the name indicates, we're about to start dealing with Bayesian models where we have more than one parameter. With our random coordinate globe toss example, we just had the one parameter, but now we have the much more realistic case where we have several parameters. If you think of a regression model, you usually have a whole bunch of parameters, a whole bunch of beta terms, and a variance component to estimate your residual variance. So we're trying to get more and more realistic as the time progresses. So if we look at the road ahead, we just came out of one parameter models, and I'm going to go ahead and take multi-parameter models as far as grid approximation is going to let me take it. This is going to be the last unit where we use grid approximation, because then I will be moving to Markov chain Monte Carlo. In fact, that's the next unit. And that's really where we're going to stay. Our author doesn't introduce Markov chain Monte Carlo until later in the book. I think it's a very important topic to introduce now. We're going to do it slightly differently. I'm not the author of the book. Maybe I wish I was, but I'm not. And we're going to do it slightly differently. And I think this is going to be a okay thing to introduce right after grid approximation. Okay, so big takeaway from this slide, we're going to do multi-parameter models two ways. In fact, we're going to do them the grid approximation way, which is when most of this this unit is on. And then we will start to move into Markov chain Monte Carlo, or MCMC. The other thing we're going to do in this unit was to begin to introduce some typical Bayesian plots and post hoc analyses. So for example, trace plots are very, very common type of Bayesian figure, but I will show you how to look at it and what to look for. And we will be talking about, once you estimate your posterior, what are all the fun things that you can do because you're a Bayesian now. And we're even going to see a sneak preview of the BRMS package, because we're going to check our work. We're going to do something using grid approximation, which is just like tried and true and sort of I'll call it a dumb and slow approach. And then we're going to use the pretty shiny package to go ahead and tell us if we did a good job. So I am staying just, adjacent to the book. You don't need me to read the book back to you. So the book covers an example with two parameters and a normal distribution. This is a distribution for height, I believe. So you can read the sections of the book that cover this example, and that will give you the two parameter case. In this lecture, we're going to take it one step further, which is a three parameter case. So one thing to start to think about is that with two parameters, we have a three-dimensional posterior. So here the parameters are the mean and the standard deviation of height. I think this is height in centimeters. And so jointly, the posterior for these two parameters is going to look like an anthill. So this is a three-dimensional anthill. And you can see that it's slightly squashed, right? It's slightly elliptical in this direction. So it's not quite a normal distribution in three dimensions. So the interpretation is that the most likely values for our two parameters are right there, as sort of the color indicates. Like I said, we are going to work on a three-parameter case. And the motivating data set comes from limnology. Until I started working with a limnologist, I did not know what limnology was. Limnology is the study of lakes. And our data set comes from the Lagos NE database that is publicly accessible. You can click the link and play around with it. There's also an R package as well, if you'd like. And my collaborator, Dr. Sarah Collins, she was in charge of putting together this database. So thank you to her for creating a wonderful database. We'll be working with log Secchi. Log Secchi is a measure of water clarity, water quality, if we're thinking about it simply. And It is the number of meters that you can drop a disk into the water, and it's the number of meters that you can still see the disk. So the larger the Secchi value, the farther through the water you can see this disk, the more clear the water. So this log transformation, you know, we use log transformations all the time. They help with right-skewed data, but the problem is that sometimes when we perform a log transformation, we get a left-skewed data set. Left-skewed. This is left-skewed because our left-hand tail is larger than the right-hand tail. And we have our wonderful QQ plot here. And we see that, you know, we have pretty non-trivial deviation from normality right over here. So this too is indicating a left-skewed data set. You know, deviation right over here is within the expected bounds, as is at the other end of our tail. So we're dealing with a left-skewed data set. What are we to do? Well, luckily, since 1985, we have what is called a skew normal distribution. And it's sort of how it sounds. A skew normal distribution is like a normal distribution, only it has an extra parameter that controls the skewness. So if our extra parameter alpha is less than 0, we are left skewed, and you can see this, I don't know, call it cyan curve. That curve is certainly left skewed. If our alpha parameter is greater than 0, then we get a right skewed data set. And you can see this sort of navy blue curve for a right skewed case. And finally, the regular old normal distribution, usual normal, is a special case of the skew normal. That's the beautiful thing, is the skew normal is more general than the normal, yet you can still recover the typical normal case if this alpha parameter is exactly 0. And that is the familiar bell curve that you see right over there. So thank you, Dr. Azzolini, for a wonderful, if you would like to read the original paper, there is the link. You're not required to, but just want to give credit where credit is due. They have published a few updates since 1985. This is just the original, so I'm citing the original. Okay, with 2 parameters, our posterior was 3-dimensional. You saw the anthill a few slides ago. With 3 parameters, our posterior is 4-dimensional, 4-dimensional posterior. Because we have, if you think about axes, we have one axis for this parameter, xi. This is xi parameter. This is one axis for omega, one axis for alpha, and then the density itself as the 4th dimension. How the heck are we going to visualize a 4-dimensional object? Leave it to me. By the end of this lecture, you too will visualize a 4-dimensional object, drug-free. So, skew normal distribution. Let's look a little bit more formally at the skew normal distribution. So I don't want to spend too long on this. The big idea is if you're looking at this kind of distribution function, you're trying to gather what the different parameters do. Here, let's start here. Our 3 parameters, C, the location, omega, the scale, and alpha, the shape, location and scale are not the mean and the standard deviation of the data. So you can't think of location and scale as the mean and the standard deviation of y. Yet, if you look at the inside of these 2 functions a little bit, it should remind you of sort of a pseudo z-score. I can't spell the word pseudo. Pseudo z-score, right? Because we're taking our variable, we're subtracting something that acts like a mean. It's not the mean, but it acts like the mean. And then we're dividing by something that acts like the standard deviation. It is not the standard deviation, but it acts like the standard deviation. So we see this pseudo z-score. I can just write that out a little better. Trouble today. Trouble. Pseudo z-score. You see it here and here. And so this first distribution, this little phi, is actually the normal probability density function. That's what little phi is. So this is just the normal PDF. The usual normal PDF that we evaluate at this pseudo z-score, and then we multiply by this big phi is the normal CDF, the cumulative distribution function. I am not going to formally define it. It finds the probability that we are below a certain value of the variable. It essentially is a distribution of percentiles inside of a normal distribution. Derivation is left to your mathematical statistics class. And I've already defined what this is, our pseudo z. So we're taking a probability density function of a normal distribution, we're multiplying it, but a cumulative distribution function of the normal distribution by taking the PDF and the CDF, multiplying them together, we get the skew normal distribution. There, inside of the CDF, is the only place where we see our skewness parameter, our shape parameter, alpha. So this is going to be our likelihood. Just to review, the reason why I'm using a skew normal is because I am trying to model Secchi data, and our Secchi data is certainly left skewed. So I don't expect a normal distribution to be appropriate, but remember that I can recover the normal distribution if we'll recover the normal, the usual normal, if alpha is 0. So that's what we call, well, it's an empirical question. It's an empirical question. How likely is it that alpha is 0? We can ask that question once we get our posteriors. How likely is it that our data, the population of Secchi that our data came from is actually not left skewed? We can ask that question as well, right? We're talking about population parameters, not sample statistics here. Okay. Likelihood and priors. So this just kind of follows directly from our previous unit. So this essentially says the same thing, but I'm just being super formal that I'm saying all 100 observations are IID, independently and identically distributed from a skew normal with these parameters. C is the location, omega is the scale, alpha is the shape or the skewness parameter. Now we get to have some fun because we have to set priors for 3 parameters, not just one. And only one of them, we have some kind of intuition and logic. Where would this intuition and logic for alpha come from? Right here. So you can see, for example, the shape of our distributions for different values of alpha. So this tells me, okay, when alpha is at -4, it looks like I'm covering, roughly speaking, values from -3 to 0. Alpha is -4, I'm covering -3 to 0. Alpha is 4, I'm covering 3 to 0. My data roughly spans from 2, or from -1.5 to 2, also left skewed. So I am not too worried about alpha being less than -4 or greater than 4. This image, by the way, is from Wikipedia, our wonderful, wonderful resource. So based on that, I am not too worried about alpha being, I think alpha will be within -4 and 4. Now, of course, we can set all kinds of distributions inside that range, including a uniform from -4 to 4. But on our discussion boards, we were having a debate over hard constraints versus soft constraints. And you can set a uniform from -4 to 4, and those would be hard constraints. No matter what your data shows, if you set a uniform from -4 to 4, there is no way that alpha could be outside of those bounds. And so we're going to avoid that. So even we can argue all day about how to set this one prior, but at the end of the argument, you will still be left with priors for the other two parameters, C and omega. And again, these are not the mean and not the standard deviation. So you can't even figure out what is a typical value for these. You can't take the mean of the data and say, all right, I'm going to center my C prior around that value. You can't take the standard deviation of the data and say, all right, I'm going to make sure that the standard deviation of the data is a typical value inside the prior for omega. So how do we do it? Well, prior predictive simulation. And again, I'm just telling you that for the two parameter case, you can see page 85 of our book, figure 4.3. We're going to do it for our three parameter case, that much more exciting. Here's the big idea. We have a wonderful computer in front of us. We can just generate random samples of the parameters. From the collection of priors. We no longer have one prior. Our three priors will interact, multiplicatively in fact, on the natural scale and additively on the logarithmic scale. So it's important that when you introduce uncertainty into a prior to see how that propagates into the likelihood. So what we do then is feed these random samples of the parameters into our supposed likelihood, in this case, the skew normal, and investigate what our fake data looks like. So what we're asking then is, can we specify priors to create this fake data world such that the data we observed are a plausible realization of that world? Can we create priors to make this fake world such that what we observed was a plausible realization of that world? So that is inherently a subjective question, and our author, I think, would agree with that, the way he approaches prior predictive simulation. So first, we need to generate random samples from the collection of priors. We need a starting point. Before we can start tuning our hyperparameters, we need a starting point, but that's okay. That's okay. Location, let's think about our parameters. Location is defined for all real numbers. So -infinity to infinity. So we have a number of distributions that can cover that. Normal distribution is typical. Normal distribution is typical because we like the hyperparameters of a normal distribution. We like being able to set the mean and the standard deviation, right? But some people consider the t-distribution and the Cauchy distribution if they want to introduce heavier tails. Heavier tails means we're going to get a more conservative result. Conservative result, right? Because we will a priori introduce additional variability into our prior. Now, is that a good idea? Prior predictive simulation can tell us. Now, the next parameter, the scale parameter, is defined for all positive real numbers. If we go back and look at where our omega, our scale parameter, appears, it's in a denominator, it's in a denominator, and it's in a denominator. So it better not be 0. It better not be 0. And it cannot be a negative value based on its definition. So we need a distribution that covers all positive real numbers. So sometimes you will see people use the uniform distribution for hard constraints. In fact, our author, in his example, uses like a uniform 0, 50 or something. So we could do that. We could set a uniform wide enough to really allow all reasonable possibilities. But you know what? I don't want to teach you to do that because the world is moving towards soft constraints. Because I too would be nervous about setting the bounds of a uniform and completely saying that anything outside of that is impossible to appear in the posterior. So something like an exponential, a half normal, are typically used for all positive real numbers. Again, as we're talking about exponential and half normal, you think of distributions that have a heavier tail. Think of half t and half Cauchy. By the way, what is this half moniker? So if x has a normal distribution with whatever mean and whatever variance, standard deviation, then the absolute value of x has the half normal. And I've seen it be half n, I've seen it be hn in the literature, I've seen it written out as half normal. I've also seen it like this, n plus. And that always confuses me because if the print is small enough, you don't see the plus and you're like, you're setting what distribution to your standard deviation? Watch out, right? Statisticians like to keep themselves in business by using different notation. So just read your papers carefully, guys. All right. If our x is normal, then the absolute value of x is half normal. And you can apply that to the other ones. If x has a t distribution, then the absolute value of x has the half t distribution. Okay. Getting real exotic here. Let's bring it back. Remember that alpha was the only one that we have any idea about. We really think those values are going to be between -4 and 4 based on the image from Wikipedia. It's not bad though. That's, you got to get your information anywhere you can. So again, this alpha parameter is defined for all real numbers, but we really think it's going to be between -4 and 4. And the same thing, the normal distribution is typical, but don't get carried away. Don't get too like, oh, I think it's going to be a Cauchy. Anything is possible. Well, in the end, we're trying to make a world from which our observed data could be a plausible realization. All right. So it's time for us to delve into R a little bit. Put my stylus down. Uh-oh. All right, let's put my stylus down in a different place. Here's R. This is the code that you'll have up on while courses. I just finished making this histogram on line 9. First things first, the skew normal likelihood is not a standard likelihood that is included in R, so we need to download this VGAM package, and that's what I'll call right there. I don't need it to try some of my priors. So here is my first prior. Remember, I'm taking random values of my parameter, of my Xi parameter, that's the location, from a normal where here are my hyperparameters, 0, 2. Now, we can start there. That is where I will end up, but I will show you what happens when you start to ratchet up that uncertainty. Right here, I take random samples of my omega, my parameter, my scale parameter. And I mentioned that you can use a uniform. I mentioned that you can use an exponential. By the way, the mean of the exponential is 1 over the rate. Mean of exponential is 1 over rate. And annoyingly, this statement depends on how your exponential distribution is written. I'm just going to keep it there. But the way I have it written, the mean is 1 over 1, or 1. So my scale parameter, the average of these random numbers, is going to be 1. Here, I'm making the half normal. So you will see the absolute value of a normal distribution. And in a half normal, when you're setting a half normal prior to something, you only play with the standard deviation of that prior. So you leave the mean at 0, and you're only playing with the standard deviation of the prior. Finally, here is our alpha samples, the samples of our alpha parameter. I'm going to use a normal, and here I am baking in a little bit of information into my prior. Let's go back to the data. My data are left skewed. That is just true. What I observed is what I observed. By the way, this database has been validated. What differentiates it from others is that this has been validated. So we really think that this log seki is left skewed. So why not bake some left skewness into the mean of my prior? But I don't want to disallow that the underlying population distribution is actually symmetric. So you will see what I'm doing here. I'm saying normal with a mean of -2 and a standard deviation of 2. So that definitely bakes, centers that prior in the left skewed world, but allows plenty of possibility, prior possibility, of capturing 0, which will allow the underlying population distribution to be symmetric. So this is where I ended up. Let me run this case that matches what I have on the other slide. Okay, so this just independently creates our samples of priors. If you recall, we did something similar in our first activity. And now we feed them in our skew normal log likelihood. And again, this is what you need the dgem package for. You also need to take the same number of samples, some large number of samples, 1,000, 10,000, 100,000. 10,000, that would match what the author does in his example. I just went with 1,000 because that's just what I did. All right, so here is my fake data set, my prior seki. So this is the world assumed by my priors. And I'm going to investigate this using a histogram, using a density plot, which is just a smooth histogram, and a QQ plot, because I want to make sure that my fake data is also left skewed, because my real data is left skewed, right? So here on the left, I have my prior assumed log seki values. What I'm looking for there is that what I have observed could have reasonably come from this distribution. Let's go back. What I've observed is left skewed and varies between 2 and -1.5. Yep, that 2 will be right over here. -1.5 will be right over here. There's my left skewness. There is more uncertainty in my prior than what I've observed in my data. If you remember what I was telling you about weakly informative priors, you look at what you observed, and then you say, I'm going to make a weakly informative prior. So I'm going to bake more uncertainty into my prior than what I have in my data. So I am okay with what I see on the left-hand side. The middle just smooths out what you see on the left-hand side. I just wanted to show you that. Our author makes this kind of plot. I want to match him whenever I can. I'm not sure it has more information than the histogram, but there you have it. There's the density plot, lightly left skewed, more than covers our data and has more uncertainty than what our data has. Here is our QQ plot. Now remember, our QQ plot is based on 100 observations. This QQ plot is based on an arbitrarily large number, which is 1,000. But what I'm looking for is that there is some left-hand tail here. There's our left-hand tail. So there is some left skewness that is induced by our priors. I like that because I think our data came from a left skewed world. I want to make sure that this left skewness appears in my prior. And where does it come from? You remember that I set the prior for the parameter that controls the skewness to have a mean of -2. But I'm not excluding symmetry from consideration, not at all. Okay? So I think these are pretty good weakly informative priors. Let's see what happens when we start playing around with this. So what I see out there sometimes is people start getting crazy with these standard deviations. Sometimes in the literature, you'll see people say, oh man, I don't know anything. never seen nothing, never seen a lake, never swam in a lake, never drank a lake. I don't know nothing. I'm gonna set this prior standard deviation at like 100. Yeah, uninformative. Here we go. So I just changed that one prior. Let's see what it does as we investigate its effects. All right. Well, first of all, what we observed, let's go back to what we observed, ranges from 2 to -1.5. No, I don't think that Secchi can't possibly be outside of that range. But I also don't think that log Secchi can be 200. That would probably be the depth of the deepest lake in the world. Secchi is the number of meters you can see a disk as it drops down into the water on the log scale. So exponentiate that, right? You're getting probably deeper than the deepest lake on Earth. So this right here would be a prior maybe for Secchi, but not on Earth, a different planet, guys. Also, look, when I changed that prior, it completely washed out my left skewness. According to the QQ plot, that histogram is not very much left skewed. So I don't like this world for 2 reasons. One, it doesn't model log Secchi on Earth. It introduces ridiculous values into the distribution, and it has washed out left skewness. So don't do that. Let's flip back. Let's put this back to 2, where it was. So this is, by the way, a very iterative process, but that's one way that I get comfortable setting priors. Once you go through this process a few times, you kind of learn what parameters are more or less sensitive to what parameters are more or less sensitive, and so you focus your attention on those. All right, here is our exponential. So remember, the mean is 1 over the rate. So to increase this mean, I need to reduce the rate. So there, my mean of this distribution, I can just verify this for you. The mean of that distribution is 1 over 4. That means 4, or approximately 4. I can get to 4 if I take more than 1,000 samples. There it is, there's 4. So what I'm baking into this prior is that our omega will be right skewed, right? It has to be, because it has to cover all real numbers excluding 0. And the mean will be 1 over 0.25 or 4. All right, let's see what that does. My prediction is, well, not very good. I don't know if it's messed up on my screen, so let me make sure that, all right, let's try that again. All right, there it is. I'm getting something left skewed at this point. I'm happy about that. But I'm getting something that is much more than that. I'm getting something with pretty heavy tails. Look, I also have this unruly right-hand tail, and I get something a little bit more left skewed than I think my data supports, right? I'm getting something that is very left skewed with a very heavy tail. My data are left skewed for sure, but only slightly left skewed. So I don't want these heavy tails in the world that has produced my data. So that is too much, too much. Let's go back to R. Finally, let's put this back to 1. By the way, you can play around with these. You can figure out the priors that make you happy. But now you have a vehicle to do this, and you know what question to ask. Could my data have plausibly come from this distribution? If you're comfortable answering yes, then you have my blessing. Here is one way to mess it up. What if we set the prior for our skewness parameter to be a positive number, like a 5? So you know this is going to mess it up, right? You know this is going to mess it up. Though not as bad as what I expected, but our data, first of all, this data set is now right skewed. Our data is left skewed. And this data allows a whole lot of positive values that are not totally in the tail. Our data does not have a whole lot of positive values in that tail. So would this be the worst thing in the world? No. but this is also not the most efficient prior. And this prior imposes right skewness where we need left skewness. Tell you what, I am boring you with these details. I have given you this code. You can play around on the discussion board. Go ahead and share what you find. Maybe there's another one that I haven't thought of. Feel free to take a look at how this is done in the literature and share on the discussion board what you think. Okay, we're ready to move on. Ready to move on. I want to finish this lecture with some beautiful four-dimensional eye candy is what I'm going for. So to answer the question, could our observed data be a plausible realization from this fake distribution? I think yes. But it's subjective, so if you're free, priors are subjective, but they make us be very upfront about our assumptions. When you're writing a Bayesian paper, you must not only specify the priors you used, but also provide just the justification for those priors. And this can certainly serve as justification for why I picked these priors. Okay. Now I'm starting to write log likelihood and log priors because it really doesn't matter. On the multiplicative scale, I can have a likelihood, and then remember what the posterior is proportional to is the likelihood times the prior. On the log scale, what the posterior is proportional to is the log likelihood plus the log prior. So it doesn't matter that all of these things apply whether I'm working with a log likelihood or the regular likelihood, whether I'm working with a log prior or the regular prior. So let's take a look at what we have actually created. Here are the log priors. So that's why we have negative numbers on the y-axis. So these even more are not probabilities, but there still are plausibilities, relative plausibilities. Remember, we imposed a normal 0, 2 prior on our location parameter C. You can see that 0 is the most likely a priori value, and then on the log scale, it drops down after that. Here's an interesting one for you. We imposed an exponential distribution, exponential 1. But exponential 1 distribution actually looks like this. That's the exponential 1, because in general, the exponential distribution looks like this. Whatever the variable is here, right? X, omega. And so when you set the mean lambda to 1, you get this. And you take the log of this quantity, just get negative omega, which is a line. And that is what you then see on the log scale. Everything that I said about the location prior applies to the shape prior. The most likely value is -2. That's what we should set with this hyperparameter right here. And that's what we see when we're plotting our priors. Getting closer to visualizing a 4-dimensional prior. I have not tried a 5-dimensional prior, and I'm a little scared to be honest with you. If you will do it or you have done it, please do tell me on the discussion board. I would love to see it. So notice that this statement is basically the statement from Unit 1, but just with vectors. Now with vectors. So our parameters now have a vector. There's our vector. Maybe technically it's like this. You get a row vector, column vector, doesn't matter. So formally speaking, here's a little trick that I don't think enough people in the literature talk about. Formally, our posterior is proportional to, here is our likelihood, times this right here is the joint prior of the 3 parameters. I repeat, it's the joint prior of 3 parameters. But we almost always assume that the prior distributions are a priori independent. So if we assume that our prior distributions are independent, we can write the joint as the product of the univariate distributions. That's a small assumption to make that really helps us out. Because boy, do I not, I want to set a prior for each of these. I wouldn't know how to set a prior for all three of these at the same time. So we make this assumption, and then we can basically incorporate these priors one at a time, just like that. And finally, the next sleight of hand is we take the log to work on the log scale. So this is our log prior, log posterior. It is proportional to, here is the log likelihood, plus log prior 1, plus log prior 2, plus log prior 3. We really like addition because it keeps things computationally stable. Computationally stable. When your prior starts grabbing the things in that outer tail and starts to multiply by other things, the computers don't like that. We're going to work on this logarithmic scale because it's going to be computationally stable. So this is the world, right? You can see how it doesn't actually matter how many parameters we have in our model. Here we have 3. What if you have 33? Okay, well, if you have 33, then your prior, keep saying prior, your posterior is proportional to your likelihood, depending on all 33 of your parameters, times the joint prior for your 33 parameters that you're going to assume is a priori independent, and then you're going to basically specify a single prior distribution for each of your 33 parameters and add them all together on the log scale. Cheese it, you're done. You're a Bayesian now. I don't want to lose sight of the fact that we're talking about what the posterior distribution is proportional to. To get to the real full posterior distribution that integrates to 1 and is therefore a real distribution, we need to take the numerator and divide by this 3-dimensional integral. And we really don't want to do that. We don't want to do that because once you integrate out your xi, omega, and alpha, it's now a constant, right? Denominator does not depend on your parameters, so denominator is constant. Spelling. Freudian slip. Denominator is constant. So that's why we don't worry about it. It does not change the shape of our posterior. It does not change the relative frequencies inside our posterior. It just moves the entire shebang up and down. Finally, by IID, because we assume IID, we can compute the likelihood for all n observations, the log likelihood for all n observations by summing the log likelihood for each observation, given a set of 3 parameters. So I am telling you to look at a certain set of lines in the code that I will show you in a second. And so I don't want to, yes, we're ready to look at this in R. So we're heading towards the grand finale that I'm setting myself up for, which is a view of our four-dimensional posterior. You can tell I'm very proud of it. Hey, you got to be proud of the stuff you do, right? And especially in 2020. Here we go. Clear this off. By the way, if I haven't showed you, GC is a garbage collection function in R. We're going to be dealing with some pretty large objects, like in the order of 1 million things in the object. We really ought to clean up the memory so that things don't crash on us. In fact, I'm like 40 minutes into this talk. If R crashed right now, I would not stop this video. I would just reboot it and have you watch me do it. I'm into this. I'm too deep. I'm in too deep. We're dealing with grid approximation. I'm going to set up my grid approximation to be wider than my priors, right? So if you remember for C, I set a normal 0, 2 prior. So arbitrarily, I've picked -5 to 5 as the grid for it. You know, is it wide enough? You can modify it and see what the effects are. I don't think the effects are going to be that large. Here is the omega grid. Remember, positive real numbers, excluding 0. So you got to start at a small number. You can't start at 0, otherwise that likelihood won't compute because we'll be trying to divide by 0. To something, right? In a grid approximation, the bounds are arbitrary. Finally, the bounds for the skewness parameter, alpha, I'm not making them symmetric because the data are skewed. If the data are skewed, I'm not going to evaluate my posterior for an alpha of 8. The data are skewed, so I'm only going -8 to 2. Arbitrary decisions, you can play around to see what they do. You have access to this code. Here's an important step. Each one of these lines sets up the unidimensional grid. I need to have a 3-dimensional grid. So I use this expand grid function, and here is what it does. First of all, it is over a million points inside of this grid. Because I'm going to here hold my omega and alpha constant and just change C. And then all the way down to when I hold omega and shape constant at a different value at the end of their grid and still continue changing C. And that's why it's so large, right? It's a Cartesian product. It's a Cartesian product of our 3 univariate grids. Okay, now I'm going to evaluate my priors for the 3 parameters. If I go back, these are the distributions of my parameters, right? I'm going to evaluate my prior, my normal 0, 2, for the different values of C. I'm going to evaluate my exponential 1 for the different values of omega. I'm going to evaluate my normal -2 and 2 for different values of alpha. And that is what I'm doing right here. One little change, notice this, log equals true. So I'm baking in that these are now log priors. Log priors. That is the same as taking the log of that. Log of a D norm it's the same thing. It's just a little bit neater to set log equals true inside. So here is my log priors, my univariate log priors. I like setting univariate priors and then combining them all together just like this because I've assumed my priors are a priori independent. So this next plot, don't tell me I didn't warn you because we're plotting a million observations. These plots take a long time. So this just produces what I have in the notes up here. Don't just quickly reproduce it because it will just take a long time, might even crash your computer if you don't have enough memory. We're at the trickiest bit of this code, which is computing the log likelihood. A few things make it tough. First of all, we have the log likelihood for n observations that we have to evaluate at a million grid points. I don't want to use a single core to do this. I'm going to do this what is called in parallel. A computer has 8 separate processors. Your computers likely have something like 3 or 4. Maybe you have a much better computer than me. You have like 18 processors. That's great. You can use all of them. Here is what our log likelihood looks like. It's a log likelihood because I have log equals true here. It's the D skew norm, so it's the skew normal log likelihood for my data, my SECI data, for a single set of parameters. I'm picking the first C, the thousand omega, and the millionth shape. Here's what I get. I get 100 log likelihood values, 1 per data point. So here's the trick. Per IID assumption, I can just add them together and make the log likelihood value for this set of parameters. And I'm going to do this in parallel. do this in parallel. I'm going to use the for each package and the do parallel package. Would this work if I did this single threaded? Yes, but it would take a very long time. Already this took about 10 minutes to run. I will not run it in front of you. I have uploaded a pre-computed log likelihood that you can download and run this on your own time. I mentioned I have 8 processors. I'm using 6 of them because I want to run my email and I want to have an internet browser open as well. So yes, I could have used 8, but it's not recommended. Here's what happens inside. Here is the setup. The do par tells R to use parallel processing for this. I have to tell it to use the vgam package for this dskew norm function. And now, here is where the iteration occurs. See these i's in here? So I'm going to be iterating over all 1,030,000 different sets of parameters as defined by my grid. And I'm going to sum over the log likelihood values for all 100 observations, because I want to end up with a single log likelihood per set of parameters. So I run this. This took about 10 minutes on my computer earlier today. This stops the cluster. I have saved my computed log likelihood for later, and I will now just load it. All right, there's my log likelihood. I can check if I have any NAs. If I, for example, included 0 as a possible grid point, I might have gotten an NA, especially if I use that uniform 0 to something. I do not have any NAs. And you will notice these right here are log likelihood values. By the way, they're all negative, which sort of matches up to this scale right here. You're thinking relative plausibility, not probability. How many do I have? I hope I have as many as I have sets of parameters. I hope I have as many as I have sets of parameters. Yes, my grid is 1,030,000 rows and 3 columns, 1 per parameter. I am doing good. Now, here comes this step. On line 106, I'm taking my log likelihood, I'm adding log priors. As a quick reminder, up here, I said log equals true inside of each prior. So there are now log priors. And that means that on this line, on 106, if I go back into my notes, my log posterior is proportional to my log likelihood plus all the log priors added together. And that is what I'm doing on this line right here. Finally, this is my log posterior. I need to convert it to anti-log it. And the way I anti-log it is with this exponential function. So you will notice what I do is I anti-log numerator and then use the trick where I normalize by the sum, as we've shown you in Unit 1, as the author does as well. So anti-log, and then normalize by that constant. Prove to ourselves this is now a real 4-dimensional distribution. Does it integrate? So sum is just an approximation of integral. To 1, it does. We are now working with this post object is a real 4-dimensional distribution. Now, it's about time for me to stop talking. And I'm about to leave you with a beautiful 4-dimensional plot. How the heck are we going to visualize a 4-dimensional object? So, if you think about a room as being 3-dimensional, every axis in this room is going to be one of our parameters. And then you imagine a cloud in the middle of the room. That cloud has variable density. The densest portion of that cloud is going to be where those parameters are most likely. The most diffuse portion of that cloud is going to be sort of the tails of our distribution. So I'm looking for something that looks like a cloud. So one more little thing we have to do. I don't want to be working with 1 million parameter values. Remember, my grid has 1 million parameter values. I'm going to take a sample of my posterior. This is going to be for computational purposes and also exactly what we do when we perform a Bayesian analysis. We very rarely work with the full posterior. We're going to be sampling parameters from the full posterior. here I'm setting the seed number to just come back to this exact same sample. And I'm taking, with replacement, 50,000 parameters, 50,000 samples. Each sample has 3 values, right? C, omega, and alpha. And the probability of making it into my sample is equal to the posterior probability. So the more likely in the posterior the sample, the more likely it is to make it as one of the 50,000. The less likely a set of parameters is inside the posterior, the less likely it is to make it into the 50,000. So here is my sample of 50,000. By the way, I can just run a quick summary of this sample. And hey, look, here are my Bayesian estimates, right? I have now taken a sample from my posterior, and here is the posterior median estimate of C. Here is the posterior median estimate of omega, the posterior median estimate of the shape parameter. I promised I would leave you with a plot. I am mostly flexing here to plot in 4 dimensions. You will not be required in your homework assignment to plot in 4 dimensions. You might have to plot in 3 dimensions, but not in 4 dimensions. There's a number of arbitrary choices that I'm making. I'm going to be making a kernel density, a 3-dimensional kernel density, right? The more dense the observations that made it into my sample, the higher the density will be there. I'm trying to recreate that cloud that has the greatest density where the posterior probabilities are large, and lower density, more diffuse, where the posterior probabilities are low. So when I run all this, and I will admit that this might not work on a Mac. We're going to be using the MIST 3D package, the RGL package, and the Viridis package for colors. So when I run this, it's going to pop up a different window with our cloud. And I forgot to run the packages, so that was anticlimactic. I'm really happy you guys saw that. So again, we're going to try this again. Let's run it, the sample, grab my sample. I'm getting the same sample each time because I've set my seed. It's my birthday, by the way. I don't expect a present. Because your attention to this will be my present. And you can see that it's taken a little bit of time to run. We are making a 3-dimensional cloud. And it has popped up a window with a 3-dimensional object that I can now interact with. So here's my room. The axes of my room are defined by the C parameter, which is the location, alpha parameter, which is the skewness parameter, and omega, which is the scale. And I can now rotate this to my heart's desire. I have assigned the density of this. Yeah, I've assigned the density of this right there to be represented by different colors. And that's why the inside of my cloud, where the density is higher, is a different color than the outside of my cloud, where the probability, the posterior probability is more diffuse. So what we're picking off is basically right in there is the most likely combination of my 3 parameters. Now we can project this 4-dimensional object, 3-dimensional object, this cloud, this way. We can project it this way and project it this way to get what are called marginal distributions, right? If we just look at it from this direction right here, I'm getting a distribution that only depends on omega and C. I'm getting a little ahead of myself. So to summarize and close out this fairly long lecture, and I really do appreciate you sticking with me, we set out to make a realistic example. I wanted to expand on what McElreath does and go from 2 parameters to 3 parameters. And I thought about how it would visualize a posterior distribution of 3 parameters. And I thought of the cloud that is densest where the parameters are most likely and diffuse where the parameters are less likely. I computed a full posterior, and then I took 50,000 samples with replacement from that posterior, where I let the posterior probability be the probability of being included in that sample. So this is the three-dimensional kernel density of those samples. And we can now pick off the combination of parameters where the posterior is densest, right in there, right inside the middle there, kind of a elliptical, flat-ish cloud, right? This is not a spherical at all. It's not spherical at all. So this is what we have. I can certainly play around with this all day, but I am gonna let you guys go. Thank you so much for your attention. We will keep going with this unit next time. So have a wonderful weekend. Please stay safe and play around with those priors if you'd like. Goodbye.